I built this graphic as part of a larger project. I think a lot of the people looking at that project will have seen this before, but if you haven't, I'll give you a quick tour. This left column has various simple functions. These are common examples because you can use these to build up other things. One, function that never changes, x, the function that's exactly the same as its input, x squared, x cubed, x to the fourth, with nice pictures to go with them. The blue part is the original function. The second column says, what if we add some small thing to this? How will a small change in the input affect the output? If you haven't seen it before, x is a real-world number. Something like I have 10-foot ceilings. Something like I have to drive 10 miles to work, and it takes me 20 minutes. dx is for smaller numbers, things that you're not meant to notice. What's the frame rate you're watching this at? What's the sampling rate for the audio? How often does your speedometer update? And that's exactly what we're looking at here in calculus. We care about that little extra bit. So let's see it all visually. X to the 0 is just a point. It doesn't matter if you change the input, it means nothing. X to the first power, the change is exactly what you expect it to be. The change in the input and the change in the output are the same because the input and the output are the same. It starts to get interesting with x squared. When we compute it, we find that we have smaller pieces that, again, I've shown in normal algebra notation and in graphics notation. X cubed, very similar. And x to the fourth, well, I can't actually draw the fourth power, so I did a little bit more calculus. I got rid of the blue area before we started. The blue area is just subtracted away so we can focus on the change. That's all we really want to know is the part that isn't blue. And then I divided by dx just to get rid of it, so all that's left are some normal three-dimensional shapes that we know how to look at. The important thing here is that dx is meant to be very small. Sometimes we draw it bigger to exaggerate it, but you want it to be as small as possible. In particular, in calculus, you want to get it so small that dx squared can be completely ignored and dx to the third and whatever other powers. The idea is that this little bit by itself is only noticeable because we're staring right at it. But when you look at something that's got a dx squared in it, suddenly there's 2 or 3 small bits, and they all multiply together to get smaller and smaller. In normal calculus, all you're really looking at is the big changes. The small changes, as I said, are small enough to go away. You might notice now that there's some yellow stuff that isn't labeled. Well, in normal calculus, these would disappear because there's a dx squared. The problem is, I can't always make dx as small as I'd like. The real world goes a little bit further than high school calculus. Fortunately, I have a really simple solution. When I'm estimating things, I use one extra term. The part that was yellow is now green. So now I'm doing a little bit more work in my estimate, but it gives me a much better result and an almost perfect result. I can still ignore the red stuff. Thank you for watching.